Welcome to Chapter 9. Chapter 9 is a continuation of Chapter 8. We are going to talk about momentum and how momentum is conserved. So momentum is kind of talking about everything that we've talked about now. We're going to take mass, velocity, acceleration, force, combine them all together, and that is momentum. So when we talk about section 9.1, we have to talk about impulse and momentum. Now, what is impulse? Impulse is essentially the average force on an object and the time interval at which it acts. So if you had to put in an equation, impulse is force times change in time. Right? Impulse is also equal to the change in momentum. Right? Now, the change in momentum is used as a P, that is equal to momentum. So what you will see is this is equal to change in P. And we'll talk about that a little later down on the slide. But impulse is force times change in time. Force is in newtons, time is in seconds. Impulse, the unit is going to be in a newton second. Impulse is also equal to the change in momentum. Right? If we look at momentum, abbreviated with a P, is the mass of an object times its velocity. So momentum is mass times velocity. Now its unit, mass, kilograms, times velocity, meters per second, is a kilogram times meter per second. Now to tie these back together, if we want a change to tie these two together, if we want a change in momentum, that's your final momentum minus your initial momentum. Well, all that is final momentum is going to be my mass times my final velocity, subtracting my mass times my initial velocity. So that is the equation for change in momentum. So impulse, force times change in time, momentum, mass times velocity, change in momentum, my final momentum minus my initial momentum. Impulse momentum theorem. What we have here is this. Don't worry about anything other than this. It's saying that our change in impulse, our impulse is equal to our change in momentum. That's all the impulse momentum theorem is saying. That's all you need to know. So don't worry about writing this down. As some of you are probably writing that down already. Signs are important. We can have positive momentum and negative momentum depending on whether we are accelerating or deaccelerating and our change in velocity. Okay? So if we take a real life equation here, real life physics impulse momentum, a large change in momentum occurs only if a large impulse occurs. Well, a large impulse occurs from one or two ways. A large force over a short amount of time, or a small force over a large amount of time. Now think about the first example, where in something that you use every day as a safety precaution, where would be a large force be distributed over a short amount of time? Hopefully it's something that never has to get used in your vehicle. All right? An airbag. That is the purpose of an airbag. It takes a large amount of force and it acts over a small amount of time. An airbag distributes a large amount of force over a very short amount of time. Now, if I took that same small force and acted over a large period of time, that would be decelerating a car without getting in an accident, obviously. I'm very slowly stepping on the brakes as I go. So that would be kind of the idea of you can do it one way or the other. A large force over a short amount of time or a small force over a large period of time. That would be the impulse momentum theorem. Right. We talk about an example using the impulse momentum theorem. We have a 2,200 kilogram vehicle traveling at 94 kilometers per hour. I already converted that very nicely for you to 26 meters per second. It can be stopped in 21 seconds by gently applying the brakes. It can be stopped in 3.8 seconds if the driver slams on the brakes, or it can be stopped in 0.22 seconds if the vehicle hits a concrete wall. What is the average force exerted on each step? Well, let's go through and go with what we have. We have our mass is 2,200 kilograms. All right. Our VI, our initial velocity is 26. Our VF is going to be 0 because we are stopping. And then our time is going to vary depending what we are going to talk about. We are going to use the force or the impulse momentum equation. Force times change in time is equal to essentially change in P. Well, remember, that's equal to MNF minus MVI. So let's go ahead for our first example and plug it in. It can be stopped in 21 seconds by gently applying the brakes. Well, we're looking for the force times 21 is equal to our mass, 2,200, times our final velocity, which is 0, minus our mass times our initial velocity, which is 26. We get F times 21 is equal to 2,200 times 26. And when you do that, you get 57,300. You divide by 21, divide by 21, and the force in this first example ends up being negative. Sorry, that should have been a negative 57,300 simply because we were subtracting our initial. Our force is negative 2,700 newtons. All right. Now, for the sake of me saving all this time writing, it's also solving for if it's stopped in 3.8 seconds by slamming on the brakes or 0.22 seconds by slamming into a concrete wall. The only thing that's going to change in this equation is the time. So if I take out time, and for the second example, 3.8, we're going to divide by 3.8. And when we divide by 3.8 seconds, our force this time ends up being negative 15,000 newtons. Right. Again, for the sake of saving time and rewriting the equations, instead, it slams into a concrete wall and slows down in 0.22 seconds. Well, we divide everything by 0.22, and the force generated by slamming into a concrete wall is negative 260,000 newtons. Each one of these answers had 3 sig figs, simply due to the fact that we were limited by 2,200 kilograms and 26 meters per second, and our time was in 2 sig figs. So this concludes the impulse momentum theorem. You will be doing problems on this in class tomorrow.